Hey guys, in this video I'm going to go over how to perform a Pearson's chi-squared goodness of fit test. So this is a continuation or sequel to the previous video I did, which was on Pearson's chi-squared test of association. So I'll put a link in the description box below for that video, and that uses the same Pearson's chi-squared test statistic to test the association between two categorical variables. So in this video I'm going to go over how you can use that same test statistic to perform a goodness of fit test. So, as I mentioned here, a Pearson's chi-squared goodness of fit test is used to assess whether the sample distribution of one categorical variable is equal to a theoretical population distribution. So for a goodness of fit test, you're going to have one categorical variable that has a certain number of factor levels, and at each factor level, you're going to have certain proportions. So this is sample data, and then you want to have a model and you want to test whether your model is a good fit for your sample data. So your model is going to have the same number of factor levels, and at the population level it's going to have some kind of theoretical distribution. So it will have its own proportions for each factor level, and then you're using the Pearson's chi-squared test statistic to test if the model is a good fit for your data. So the null hypothesis for this type of goodness of fit test is that the model is a good fit for the data, and the alternative hypothesis is that the model is not a good fit for the data. To test this hypothesis, we're going to use the Pearson's chi-squared test statistic, which I have here. So it's going to be for every factor level I, you're going to take the observed frequency count minus the expected count squared divided by the expected frequency count. So OI refers to the observed frequency count, EI is the expected frequency count, and I from 1 to capital I is the number of factor levels. Once we have our chi-squared test statistic, we're going to compare that to a chi-squared critical value at some level of alpha with degrees of freedom I minus 1, so the number of factor levels minus 1. To explain how you would use it in a real problem, let's go over this example. So this is fake election data. So let's say previously there was a political election, and at the population level, this was the following distribution of how people voted. So for Republican, 50% of people voted for this party, 46% voted for Democrats, 3% for Socialists, and 1% for other. So this is your population distribution or your theoretical distribution. And then let's say there was a new election and you have sample data from 1,000 participants in the election. And let's say this was the sample distribution of this categorical variable. So this was 400 people voted Republican, 535 Democrat, 60 Socialist, and 5 other. For the Pearson's chi-squared goodness of fit test, we can test whether the election model from the previous election seems to be a good fit for this new data, or if election or voter preferences have changed. So to test that, we're going to use the Pearson's chi-squared goodness of fit test, and the null hypothesis is that this model is a good fit for the data, and the alternative hypothesis is not a good fit. And the first thing we have to calculate is the chi-squared test statistic. So for each factor level, we have 4 factor levels here. We have to calculate OI minus EI squared divided by EI. So that's going to be, for the observed frequencies, we're given O1, O2, O3, O4 from the sample data. So we know all our observed frequencies. The first thing we have to calculate is the expected frequencies for each factor level from the population. So that formula is going to be equal to the sample size times the proportion, the population proportions. So the sample size is always going to be 1,000. And the proportions we get from the theoretical population distribution. So for the expected frequencies, for factor level 1, which is Republican, that's going to be 0.5 times 1,000 is equal to 500. So that's E1. For E2, that's going to be 1,000 times 0.46. That's equal to 460. For E3, that's going to be 0.03 times 1,000, which is equal to 30. And E4 is going to be equal to 10. And now we just plug into this formula. So for factor level 1, observed is going to be equal to 400 minus the expected, which is 500. Divided by expected, which is 500. That's the first term for the first factor level. Then we just do that for the 3 remaining factor levels. So for factor level 2, that's going to be 535 minus 460 squared divided by 460. For factor level 3, That's going to be 60 minus 30 squared divided by 30. And then for factor level 4, that's going to be 5 minus 10 squared divided by 10. When I perform the algebra on those terms, we're going to get 20 plus 12.228 plus 30 plus 25, which gives us a final chi-square test statistic of 64.728. So this is our Pearson's chi-square test statistic. We're going to compare that test statistic to a chi-squared critical value. So let's just say we're comparing at an alpha level of 0.05. The degrees of freedom is going to be equal to I minus 1, which is 4 minus 1, which is 3. So if we check that critical value in R or in a chi-square table, that critical value is 7.815. When we compare our test statistic to the critical value, 64 is greater than 7.8, so we're going to reject the null hypothesis at alpha is equal to 0.05. So we reject HO at alpha is equal to 0.05. Since we reject the null hypothesis, that means that the model or population distribution is not a good fit for the data, which means that voter preferences have changed. And we are done with this problem.